And I'm really happy to be here. And like Rajiv said, mostly we meet in Chicago, and so it's for a change. It's nice to meet here. And so this is one of the areas I work in. I do a range of things, in the company, and I have now more recently started working on predictive analytics. Though I won't be talking about that right now, but we can talk offline. So as I talk, I'd like to tell you that if you have a question that's bugging you or some little thing you don't understand, feel free to ask, raise your hand. I don't want you to wait till the end and then ask questions. So, and if we can accommodate them during the talk, I'll try to do that. Okay, so feel free to please ask questions. So, the title today says, what can we learn from software failure data? And this is about failure data that we collect when we develop a product, when we develop software. So maybe I should ask people, what do you think of when you think of software reliability? Do you think about it ever? I mean, you must be all writing some code for your assignments or projects. So do you ever think of software reliability? I guess not. What do you think it is?
Should be reliable means when you are working on a software, it should not get shut down or should not crash immediately, and it should not deliver or basically disclose the information or private information to internet or some other parties.
Reliability would be consistent performance time and again. I mean, if it is performing, if it is giving certain results today, the same results with the same degree of consistency and performance should be given back tomorrow. It should be something like that.
Okay, so these are different views people have of reliability. Go ahead.
I think reliability is that first of all, the user's work should not get lost. Like we have in modern browsers every day, so that thing. And one more thing is that it should perform the way it is supposed to be performed. Like if the software is for sending email, it should send email. So, like even in exceptional cases, so proper unit testing should be done for that. I guess.
That's good. So the software should perform as per the specifications. That's what it means, right? And internally there may be some errors, bugs, and so forth. But often they can be corrected internally, and you're not concerned about that. But basically you want it to perform the function it's supposed to perform. Yeah. Okay, so let's... so what I'm going to talk about is, when we develop a product, software, we do testing. And I'll go through a little bit detail, but I just want to give you a high-level view. And when you do testing, you collect some data on failures. So that's quite a lot of data you have. And what I'm going to present is how to use that data, how to model that, to get a sense of is your product reliability improving as you're testing, or is it getting better, or getting worse, or just staying constant. So, and how close are you to removing the faults in the system? You get also a prediction of total faults. And this provides a framework where managers and developers and testers, they can all talk the same language because you have something quantitative that you can use to see where you are. So that's the general idea what I'm going to talk about. So I'll present some models. And so here's the agenda. I'll provide some motivation, talk a little bit about software. Then a brief overview on software reliability engineering, just a few definitions so we are all on the same plane. And then I'll present this case study on the software failures and then summarize. And I want to acknowledge some colleagues and Professor Gokhale at University of Connecticut. Some things I'll talk about here we have done jointly or from papers that we have published jointly. Okay, so a little bit motivation about how software is becoming more and more important. The cost of failure is huge. some examples of how much software exists in different products. Like a Boeing 787 has more than 6 million lines of code. I read that a premium class car like a Mercedes may have 100 million lines of code. And I think Rajiv gave a talk at Bell Labs where he talked about the kind of code that's in vehicles also, and he was also talking of some very large numbers. And then if the software doesn't work, there's a big cost. Some examples, there was like a food chain, retailer. They were implementing some new supply chain software and it didn't work. So what did they have to do? They had to ultimately resort to people and hire 300 extra people. And it was all because of software. Another example, some years ago, a new airport was constructed in Denver, USA. And they had a very sophisticated luggage handling system. And it was all driven by software. But it had a lot of bugs. It didn't work and it delayed the opening of the new airport because it was doing strange things to people's luggage. So I'm sure you all have many examples of this kind of problem. Here's something I got from IEEE Spectrum. It lists the company and problems with the software and the cost in US dollars. And you can see, I'm not going to go through each one of these, but the costs are huge when the software fails. And another way to think of the cost of software failure is, so if you say that failure is defined as that you abandon a project before it is delivered or shortly after, because shortly after, if the project is not performing well, after it's installed, it may be abandoned. And so, I mean, if you use some rough numbers like a failure rate of 5%, which I think is conservative. A lot of projects, software projects fail. And you can see that you can waste a lot of money. So it's really important to pay attention when you're building software, that it performs well. And in a company, if you work in a company, I mean, we're building a product like a switch. It'll have millions of lines of code. The code has to work well because our product has to work well. And because we'll be selling thousands of units of that product. So it's very important that the software works well. And so it's an important area basically. So let me just now give you a few definitions on software reliability engineering, because the models that I'll be presenting, they fall in the area of software reliability engineering. And so we talked about what is software reliability, what is reliable software. So if you look at the bottom, the kind of formal definition of software reliability is the probability of failure-free software operation for a given period of time in a specified environment. Because typically you specify, like if you're building a telephone switch, it should perform at this level, set up a call in so much time at a certain call rate, so many calls per hour. So you have requirements and your product should work within those requirements. And you have a failure when the service, when the delivered service no longer complies with this specification. And like, you know, if you're having too many when you dial somebody's phone, if you have too many calls with the wrong number, that means there's something wrong with the software. Occasionally, if there's one, it's not going to bother you. But if you have 10 calls in a row, you try 10 times, and you're getting the wrong number, that means there's something wrong with the software. Okay. So I won't go into, in the interest of time, I won't go into a lot of these details. But basically, to do software reliability engineering, we make measurements, and then we build models with those measurements and get a sense of where the software is. So I want to, I guess people here are taking courses in hardware and software, right? Many of you have probably taken hardware courses.
So I want to make a distinction between software failure rates and hardware failure rates. Maybe, is this curve at the bottom, this small one on hardware failure rate, is that familiar to some people? So, okay, let me first talk about software failure rate. So the curve there, on the x-axis is the time. So it's from a perspective of I'm building some software and then I'm going to be testing it. So in the close to the origin is the present time, and then this is time as you do testing and maybe fixing the bugs. And on the y-axis is the failure rate of the software. So when you first just build the software, it's going to have a high failure rate because you quickly written it. It's okay. So you're going to have a certain failure rate. But as you do testing, you debug, you fix the fault, the failure rate is going to drop. And in theory, for software, over time, you can reduce the software failure rate to close to zero. If you don't, you only fix the bugs found, but you don't introduce new releases or new code, right? Every time you put new code, then it's a different story. But so in theory, so the failure rate is always going down. And this includes after you introduce the product in the field, you find faults, you're going to fix it, you'll improve the reliability. Now for hardware, it's a little bit different. And I just wanted to, often people are more familiar with hardware, so I wanted to show them. With hardware, what happens is, it's called a bathtub curve because of the shape. So initially, when you have some hardware and you do factory testing, if you have some defective products, they're going to fall out. And that's called this infant mortality. And once you take those defective products out, then your failure rate comes down. And then for the useful life of the product, the failure rate is constant. And then if you keep something for very long, then physically the product starts deteriorating and it'll go out. You know, somebody gave me a good example. Actually, I think in China or somewhere. So one of my colleagues gave a good example of how to think of this. He said, you know, if you buy some cheap computer, then you are going to see this infant mortality rate also, because they didn't do all the factory testing. And you may have a high probability that your computer is going to die in the first few months or first few weeks. So, but typically for good products, this is all taken care of in factory. So this is the difference between, and we're going to focus on software. So typically, how do you achieve reliable software? There are kind of 4 general areas. One is fault prevention, and that means all these good, following good practices, using good environment, writing structured code and all those. I'm sure you're going to learn all those things in your courses, if you haven't already learned them, that what's a good way to do software. Then there's a fault removal, and that includes, inspections and reviews. These things all happen in a commercial environment, and testing. And there's also fault tolerance, which I think, in some of the advanced courses you'll probably learn at some point. But within software, there's a lot of redundancy and some diversity. And what that means is that a simple example of redundancy in software could be time redundancy. Like you perform an operation and it fails, or you don't get the result in the specified amount of time. So typically you'll retry, right? A lot of protocols, they'll retry 3 times. So that's like a time redundancy. So all of these things, they help you for the software to perform better rather than fail, because you retry. And lastly, there's this area which is a little different, fault failure forecasting, modeling. And I'm going to be talking about modeling based on data from testing. So this kind of helps you baseline where you are and whether you're improving as you do testing. And so that's also an important area for building reliable software. So there's many kinds of reliability models. I'm going to focus on the models that are developed based on data from the testing phase. So what do we do here for building these models? We collect the defect occurrence time. That means when you're doing testing, every time a failure occurs, you record the time when the failure occurred. So you have a series of, you have data points, it's basically the time. And you typically measure test time using calendar time or execution time and so forth. Then we take this data and we correlate this test data with known models, and I'll talk about those models. Those are called growth models. Because growth, meaning as you're finding bugs and fixing them, you're increasing the reliability of your product. And then you use these models to predict the remaining defects in the code and the failure rates. So it's a prediction basically. And then you use standard statistical techniques for estimating the parameters of the model. We have built a tool to do this, and I'll show you the results for that. So I just want to, maybe people here, because you're all still, most of you are students, I just wanted to give you a little overview of typical product testing. So you have what we call unit testing, which is functional testing, that if you're building a piece of software, say to set up a call or something, that whether it does that. And that's typically done by the developer. So you test for the functionality and you validate the test to certain that it meets the specifications. The next level of testing is integration testing, and it's functional, also done by the developer. But here you test whether you take multiple modules and you see whether they work well together, they interface properly. And the final type of testing in the lab is system test, which is end-to-end and usually done by a separate team, the test team, and they test with, they take many different products, put them all together and test end-to-end, given some test cases that have already been specified. And they test for many things. They use customer requirements, they create the use cases, they test for performance, capacity, stability and reliability. And the last point relates to our domain. We say use real handsets, means that you will actually use a phone to test, make calls and see whether you meet the performance requirements and so forth. While prior to that, they don't use handsets, they just use some code. So these are the types of testing, very high level view testing. Okay, so I'm going to be talking of growth models. Is anybody here familiar with this? Okay. So they're called Go models, based on the two authors, Go and Okamoto. And interestingly, this guy Okamoto actually works in our company, and he's written the books and some classical work on in this area. There are many models. The Go models are the simplest models, and they actually work pretty well. You can have more complicated models. That means then you have to estimate more parameters. You don't get all the data. So most industries use Go models. That's what we use. So let me just explain the model. These are exponential models. And so on the x-axis you have test time. On the y-axis is the cumulative number of bugs that you have found in the lab, defects. And what is the model saying? So mu t is the expected number of bugs at time t. Then lambda t is the failure intensity, the failure rate, which is just the derivative of mu t. A is something you're going to get from the model, expected total number of defects in the code. Okay, this is a prediction, alright? It's not going to be exact, because you can never exactly predict how many bugs are in the code, but it's a prediction. And B is the shape factor, which is the rate at which the defect detection rate decreases. It means as you find more and more bugs, it gets harder to find more bugs. So the slope goes down. So A and B is what you're going to get from the model. You're going to estimate those parameters from your data using this equation. So see, so if you predict A, total defects, and you know how many defects you found, then you know how many are left. And so what's the difference between these two models? They're essentially the same. There's one difference. In the second one, S-shaped, the slope doesn't go up fast initially, and that's the tester learn time. Initially, maybe the tester is new to the system, so they're learning the system, so they may not find many bugs. But once they are familiar with the system, then the two models are quite similar. Then you find it. So these are the two basic models for which I'll present results. We have used both. So I'm going to present like three basic kinds of models that we use to answer the following question. Is the maintenance process, maintenance means testing and then finding bugs and fixing them. Is it increasing the software reliability? Is the process under control? And how many failures are going to be remaining in the product? And what's the expected time to meet the requirement? These are the kind of questions the managers want answers for. So, what all are we using? The tools. We're using control charts. So one thing I want to say, you know, each particular model in itself is not like, I mean, these are not new models, control charts, or these Go models. They've been around forever. Control charts have been around forever. What we did kind of new here is we combine these and to provide a unified framework. That's kind of, I feel, the usefulness of what we did here. So we use control charts, we use the Laplace trend analysis. I'll talk about all of this. And then we use the growth models that I just described. So just to, for the case study, what are we talking about? This system that we were talking about, it had a major upgrade of hardware, OS and software. So it was quite a lot of stuff going on. And it was for prepaid services for voice. That means if you load your SIM card with money, that's prepaid, right? So this is something that has to work well, because if it's not working, you may have money on your card, but you won't be able to make a call. Well, you're not going to be very happy, right? So that's what this was. We had test data for over 200 days, and then we had acceptance tests for 52 days and operational tests for 45 days. This was quite a long period of test. It's not often that you have so much data, but it gave us good data for modeling. So in that sense it was, but it's not really typical in terms of that. So first thing I'm going to talk about is the control charts. And we use the control charts first to identify periods where the failure detection and failure correction, are they within some control limits? Because you expect some variation, which is normal, like random variation. But you want to know if the variation is outside of the control. That's what we use this for, to identify periods that were outside the control limits. So this is the formula for the control charts, where basically you get an upper control limit, you get a center line, and the center line, if your system is in control, then you can use the center line in this particular instance as a measure of the average failure. And the data that's here is the number of defects and the time period and so forth. UI is the system utilization. The best way to explain this is through an example. So this is the test period in days. Now here, this purple line is the actual daily failure rate. You're doing testing and you're finding some number of bugs, right? So that's that. The yellow line is the center line. You calculate it with the formula I showed. The top purple line, blue line is the upper control limit. So what you're looking for is when this daily failure rate goes above the upper control limit. So in this area around day 25, you're seeing some peaks. You're also seeing some peak here around day 181. So now this tells the managers, they see this chart, right away they want to know what's happening there. What was being tested, which module, who was doing the testing, and so forth. Right? So now you go and focus on those days. What happened in those days? So, in those days, we know that these modules M3 and 4 were responsible for 60% of the bugs. Then people say M3 is a complex module, we expect more faults in it, it's okay. Right? So you do that. M4 is not what they expected, so maybe the M4 code was not good. Right? So this is how you would use this data. This is one example. And the second period, I'll talk about later. So this is the different software modules and how many defects were found. You know, there are other methods where based on the complexity of the software, you have some estimate of how many bugs you should find and so forth. Okay, so you use control charts. The other thing we use is a Laplace trend factor, where before you can use the growth models, you have to know whether you are actually in a growth period. So you use the Laplace trend factor for that. And let me talk about that. So this is how the trend factor is defined at a given time period k. And so what are the inputs to this? Looks at the number of observed failures in a given time period. That's the bugs found. The cumulative number of failures up to that time. And the number of time periods during the observation period. And the thing to note for this trend Laplace factor is, if it's between -2 and +2, it means there's no trend in your data. So you can't use any growth models as yet. Nothing's happening, it's kind of noise. So you need to do more testing. If it's less than -2, that means more negative. That means you're in a reliability growth and you can use the growth models. If it's greater than +2, that means your reliability is decreasing. Even though you're testing, finding bugs and fixing them, your reliability is going down and you cannot use the growth models. Now one reason, what do you think, could there be a reason if you're finding faults, fixing them, but your reliability is going down? Can you think of why? Some reason why?
Probably in the process of fixing the bug, we are developing a code that is it's in itself containing some new bugs.
Exactly, right. And actually there's empirical data that shows, there's papers from, at least one paper from my company and the other papers. Typically, when you fix 3 bugs, you introduce 1 new bug. Yeah, so that's can be the reason. Now on the average, but if you could be in a area where you're only introducing new bugs and not, getting things fixed. Okay, so for this same data, this is the Laplace trend factor. So you can see that you can only start using the models maybe after day 75 or something. Because before that you have noise, no trend, but after that you're seeing a good trend, it's going down. So you can use the growth models. So this is good, it's good after day 75. Now here, late in your test period, you see some spike, it's going up. Even though it's not minus, it's much less than -2, but so late in the process, you shouldn't be seeing that. So later on we do investigate that. So
But in general, it's a good trend.
Question.
Yes.
So if you go back to that, so in the first few days where it's actually above +2, does that correspond to the period you were talking about earlier, where the reliability is actually decaying?
It could be, possibly that might be happening. Also, you know, in general, often early testing, there's a lot of things going on. And
Well, that's what I figured.
yeah,
Maybe more an artifact of that.
right. Yeah. That's why, so you just don't draw any conclusions from that early stuff. Yeah,
What's the frequency of the releases?
frequency of the,
You have a release every week, or no, the testing is done on.
oh, okay. So it varies by product, very much.
So for this one, then, is it daily? The complete cycle is done in a single day.
Oh, you're saying that the bugs are fixed and then a new thing is, it, okay, I don't think it's daily.
Yeah.
Now the models assume that you find a bug and you fix it, and you fix it perfectly, okay? So there's a difference between the assumption and the actual model. There are some more very sophisticated models that account for the delay, but there is a delay and it's not daily. Also depends on the severity of the bugs. Some bugs may take a long time to fix. But yeah, that's a good question. So again, here we looked at, for the trend analysis, remember I flagged period 2, and we felt this was an instability period that could affect the reliability growth. And we noticed that this one particular module was responsible for 75% of the failures. So then what this points to is, go see what's happening in that module, basically. That's the idea. Okay. Now lastly, we use the growth models. And here we're going to get metrics like, I went through some of this, like the failure intensity, number of remaining faults, and so forth. So I'll show you the results from that. But the thing to remember is you can only use these models when you have reliability growth. So this is actual data. So on the y-axis we have the cumulative number of bugs found. The wavy blue line is the actual data as you find the bug. And the purple and yellow are the two models, the S-shaped and the exponential. Actually both the models fit well. The exponential model fits a little bit better. So here we have this test period for 22 days. So we found 21 bugs actual, and let me tell you what the model predicted. So the two models, they predicted total number of bugs as 7 and 22. So obviously the first model is not a good predictor, right? Because we found 21 bugs. But so the second one then gives you a good feeling that you predicted 22 bugs, you found 21. That you have found quite a lot of the bugs, right? It's not exact in the sense of there are only 22 bugs, but it's a prediction and it gives you a good. So, and then you can also use that to forecast the failure intensity, the daily failure rate. The model does that. And it's again between 0.1 and 0.3. The measured intensity is 0.4. So it's not, in this particular case, the prediction is not that good. But still, it gives you some range for the failure intensity. And another thing this kind of analysis is useful for, you can show it to a customer. You can show your progress, how you're doing. Your model is predicting so many faults, you have found this many, and you have done so many days of testing. It's something you can show as evidence to your customer, which we do. And you can use this failure data. So you have a model, say, up to the say, testing period. Now you can use this model to predict for the acceptance period or for even for the field operation period. You can predict how many bugs you expect in the field. Same way, same model. So in this particular instance, we found the exponential model was better. But that's not universally true. It's going to depend on each particular case. And we were able to get good metrics for the acceptance test period. And now one thing, there was a spike when the product was in the operational phase, there was a spike in the failure rate. This was not predicted by the model. And the measured metrics, there was the predicted metrics. But remember, the failure intensity was lower, predicted was lower than what was actually measured. So here, what you're seeing is, so this is the daily failure rate again. Now, if you look towards the end, around day 300, you're seeing this spike, and even though it's theoretically, it's below the upper control limit, so late in your cycle, you shouldn't have these spikes. And so this is the area of concern. But by doing this, you know that you should go and see what is happening in that time. What was being tested, which module, what was the problem. Okay? So this is kind of the, the modeling we did with this particular set of data. Just to summarize, basically what we feel you can learn from this is you're sharing some concepts of modeling, and this forces all the players, developers, testers, managers to speak the same language, because you have some data to base your discussions on, rather than saying, no, this software is not good and so forth. And it really helps to improve the process. We have found this to be very useful. And you can also use it with your customer. We have also used it with our subcontractors. Like, they are developing some software for us, and they may not have these tools. We give them this tool, and we say, you give us the output. Show us how you do. So that has also worked well for us. And I think I mentioned this before. What is new about this is to combine all these methods in one framework. So this basically talks about the same thing. Let's see, I think I talked about most of these. So it helps you with the testing evaluation. You find the out of control points, which the managers want to know what's happening there. And then you can forecast this failure behavior for acceptance test and operational test. Again, the managers know what to expect in the field. Even if you get bad results, right? You're going to predict that you're going to see some failures during operational test. Then the managers know this. They can work with the customer to set the expectations. You can also already assign people, if you know you're going to see some failures, soon after the product is introduced, they can assign some people, so they're going to work on this. When you find these failures, they're going to quickly try to resolve the problem. And then you can also certify to some level, with some level of confidence, that the product is going to perform at this level with respect to the idea. Okay, some general thoughts that, there's no one model that fits everything. You have to try out different things, what works for you. In industry, the Go models are simple, but they're most frequently used, they work pretty well. And it's important to understand how your customer will use the product, because then you should do the testing that fits that use of the product, then it means you're doing better testing. And I've found from experience, if you build a model, just the process of building the model, it helps you to better understand your product. And I'm not just talking of these models. I'll give you an example from, I built some Markov models of like the system behavior, like failure and recovery behavior. And often if you just build that model and you work with the developers, you really understand how this product works. And they also get a good sense. And then you can do some sensitivity analysis on the performance and so forth. So it's very useful to build a model. I know then the hard part is getting data and so forth. But just the process of building a model really helps to understand how it works. Okay, so that's all I have. Here are some references. This last one is the classic book on software reliability. And at one time, all the authors worked in Bell Labs when we were AT&T. And Okumoto still works there with us. And if you want to look at the different growth models, there are many. I want to talk about these Go models. This reference by Wood is very good. He gives a review of these models and also explains well how you can use these models. If you have some data, how you can use these models. He used to work at Sun Microsystems, so he's written it from a very practical viewpoint, but it's a nice paper to understand, you know, because I wasn't able to cover everything here. So if you're interested in the topic, that's a nice reference. Okay, thank you very much. And if you have questions, if there's time, I'm happy to answer them. Or comments, feel free to make comments also.
Probably I'll ask a question. Sorry. You know, the data that you have